still.
The advent of mainstream affordable drones has brought new opportunities to various scientific fields. They are versatile platforms for cameras and other instruments that can be delivered to hard-to-reach locations and orient those instruments in any direction. They're relatively inexpensive and carry high-resolution and high-frame-rate cameras that can be used for data collection for many different applications. The typical sub-$1,000 drone from DJI includes a camera capable of recording 4K video at 60 Hz. That's better than a Canon DSLR, which costs just as much as the drone. The concept of using 2D imagery to make measurements is known as photogrammetry. This study utilizes the capability of drone-mounted cameras to measure the surface flow velocity of streams. Traditional methods of measuring water flow velocity utilize invasive methods, meaning that in order to estimate the flow, something must be placed into the water, such as a probe or current meter, often using a propeller. One of the problems is that placing something in the flow disturbs the flow, changing the result, causing systematic errors in the readings. Another problem with manually placed probes is getting them into hard-to-reach locations, or getting them in potentially dangerous water such as those full of debris after a flood or storm. Due to these issues, methods of remote sensing for flow measurements have been developed. Optical methods have been implemented over the last 2 decades using fixed cameras. One of the downsides is that they require the collection of ground reference points to set the proper scale of the content of the imagery. The background video you're seeing now was captured during a UNF wave-tank experiment. As you can see, there are 5 ground reference points on the ground that have all had their positions measured out. Each of their positions has been surveyed in order to properly scale the imagery. By taking the velocity data calculated using the optical method and bathymetric data of the channel, the discharge can be calculated by multiplying the cross-sectional area by the velocity. Drones are relatively inexpensive and versatile devices. They can be easily deployed over a body of water in seconds and flown either manually or following a predetermined flight path using GPS. They can automatically hold themselves in place using ground and inertial sensors as well as GPS, though there will still be movement depending on the wind. This study aims to demonstrate the viability of an aerial sensing platform based on inexpensive drones for reliable flow velocimetry. In order to accurately make measurements from the 2D imagery, it must have lens distortion removed, and the dimensional scale of the content of the image must be known. Camera and drone manufacturers often provide lens profiles so that the exact distortion of a particular lens is known and can be corrected. In this study, a DJI Phantom 2 drone with a GoPro Hero 3 camera is used. The lens distortion is removed using GoPro Studio software. The drone is flown over a body of water and the camera records video while pointed directly down. It's important that the camera is pointed straight down so that the scale is consistent across the image. If the camera is pointed at an angle, then content at the top of the image is at a smaller scale than at the bottom of the image. In order to provide a reference for the dimensional scale of the imagery, 4 lasers are attached to the drone pointing directly downwards to create a box of known dimensions in the imagery. This means that in any images taken, regardless of the elevation of the drone, accurate distances can be measured. It also means that the time-consuming process of surveying ground reference points is avoided. The velocity of the water surface is calculated by using the large-scale particle image velocimetry algorithm to track natural and artificial stream floaters. Floaters are natural or artificial particles floating in the water that can be tracked. Using the scale provided by the laser array and the image capture rate of the camera, the velocity of the floaters can be determined. As you can see in this example from the UNF wave tank, if a floater travels 4 feet over 63 frames at a recording rate of 60 frames per second, then the velocity is 3.81 feet per second. The values calculated are then compared to a benchmark current meter. Before doing the actual in-field test, the authors of this study tested the hovering performance of the drone. By having the drone hover over a grid, they tested how much the drone drifted in elevation and translation. Essentially, they were trying to see how well the drone could hold still while making measurements. On a side note, when flying the drone for the UNF wave tank study, I anticipated large amounts of drift while hovering due to wind. By tracking the ground reference points, I was able to stabilize the video to counteract both the shifts in elevation and translation. Utilizing the laser array instead of ground reference points would allow for the elevation changes to be counteracted, though not the translational changes. The authors determined that the fluctuations in elevation and translation were not significant. The stream used in this study is in the Rio Cordon natural catchment in northeastern Italy. The drone was flown over an artificial stream stretch equipped with stream gauges. It is rectilinear with a concrete rectangular channel. The OTTC2 current meter used for the benchmark values measures the velocity 3 centimeters under the surface in the center of the stream. Out of the influence of wind, therefore the velocity is expected to be larger than the surface flow. Biocompatible artificial floaters, which were brightly colored, high contrasting, and therefore easy to track, were deployed so that they could be tested against the use of natural floaters. The velocities were calculated along a profile stretching across the stream. The line is the average value, whereas the shaded regions are the standard deviation. The velocities determined using the aerial flow velocimetry platform are in line with the benchmark values, given that the benchmark was expected to be higher. The difference between the velocities determined using only natural floaters and artificial floaters was not statistically significant. The larger uncertainty of the natural floaters is attributed to longer flight times where there are more added up random movements of the drone due to wind effects and vibration. There are several things to take away from this. This study proposes a flow observation concept using a platform that includes the data acquisition and scale calibration integrated into the drone so that it can be deployed without the need to survey reference points. The drone can be flown in an automated fashion using GPS to acquire data over large areas. The system allows for surface flow velocity acquisition in ungauged and hard-to-access locations quickly and inexpensively. The substantially increased variability of the velocities when using natural tracers only poses a significant challenge to practically implementing the system, meaning that either high-contrast artificial tracers must be deployed or techniques must be developed to better track the natural tracers. In case of floods or other severe events, the increased debris in the water may be sufficient. This study demonstrates the potential of using a drone with optical sensing for surface flow measurements. The measurements performed with the drone on a small-scale stream were in good agreement with data from on-site flow sensing systems. Drones are another tool available to hydrologists and geophysicists that are rapidly improving as technology progresses, yielding more stable hovering, longer battery life, and larger payload capacity. As the drones and image analysis techniques improve over time, there's potential for the system to get even more accurate, even without artificial floaters. This study serves as a proof of concept to demonstrate that this is a technique that has promise and should be developed further.